So let's take a look at some of these transformations. So let's look at scale first. So scale is a really easy one to think about. If we have some vertex, let's consider this vertex here at position x2. We want some function scaling, which gets to this new position x2. And it turns out that for scaling, we just take whatever our vector x is and we multiply by some value. And if it's non-uniform, we're going to multiply by some non-uniform values here, right? So our function is quite a simple function for scaling. For rotation, it's a reasonably straightforward function. If we consider parameterizing these values, not as x and y, but as radius and theta. So here we have theta, right? And then we have some distance away. We can imagine that we're just going to add some alpha value to this theta, right? And then the point is going to move in a circle going around. So it looks like this, right? We have a point that's moving around. This point might move to the rotation of theta for x1 around this circle. So now what is this function exactly? Okay, where's my other slide that shows this? I thought I had another slide that gave some math on this. Perhaps it's coming later. Let's talk about, so rotation, let's just take the intuition for right now. So the point is going to move around this circle and it's going to land here. I'm going to have some function that takes it around this circle. So for translation, we have fairly simple function again. So we're just going to, if we need to move our point over by x and y, we're just going to take our point, right? So this is a vector point that's being written here. And we're going to apply it to the function. It's going to get to some new location. So this is so far fairly intuitive. We haven't written down the sort of precise math of this yet. Reflection can be another function for us. So we're going to take our point and we're reflecting across this y-axis. You know, whatever our point is, we're going to take negative of that point and it's going to move. The zeros don't move, right? So we're going to be able to reflect across x or y. There's something called shear, which makes an effect that looks like this. So our point is going to get moved over further if it's further away from the axis, right? So this is a shear along the x-axis. So things on the x-axis at y equals 0 don't move. These other things move further. And so there's some function that's going to apply this also. And we can compose our basic operations out of these more complicated operations. And the order that we do that composition is going to make some difference. So if we consider this basic square here with these vertices, if we first applied a scaling to these vertices, right? So we have an x, and we first applied the function for scaling, that would scale down to this smaller box here. And then we apply the translation 3,1 to move over 3,1. This box is going to move over here. So it's not really the whole box moving, it's the vertex. Each vertex is being applied to the function. But we're going to end up with a square here because each of the 4 vertices will end up in these places. If we reverse the order, we first did this translate of our square, then our large square is going to move over into this position. And then when we scale this larger square, remember each point is going to scale. So this point is going to go to the halfway point towards the origin, and this point is going to go to the halfway, and this point is going to go to the halfway. So if we're not at the origin at the time we do a scale, in addition to getting smaller, our vertices are going to move in towards the origin. So we're going to end up here. So these are not the same position. So the order that we apply these functions is going to make some kind of difference. So let's look at a common task we might want to do. We have some point x, and we wish we could rotate our square around this point. So how are we going to get that done? If we just apply a rotation, each of these vertices is going to move on a circular arc around the origin. So this whole square is going to move up in this direction. Do you see my pointer? That's something that you see? My mouse pointer, yeah, okay. So this whole square is going to move up in a circle going around this way. And that's not what we want. So in order to get a rotation around this point, we would first apply a translation to move our square down to the origin, apply our rotation to rotate it, and then apply a translation to get it back. So we're going to end up stacking up some basic functions to get more complicated functions that we want to have. So we can ask, how would we get each of these things? And there's usually not just a single way to do it. There's a single final function which maps from here to here, right? This is if we're defined in the I guess there's an infinite class of functions, but if we're defined in a linear or affine space, then there's one function that's going to get us here. But the set of things we can compose to get there, there's an infinite class of those. There's more than one way that we can get to this. So if we wanted to get to here, for instance, we could first scale up to get bigger and then rotate. Or we could rotate and then scale up. Because it turns out that for the rotations and scales, it's okay. You can apply them in either order. Okay, we're going to go on and talk about precise math related to this with matrix transforms next. So we're going to look at the same thing again, but with matrix transforms. So, but let me see if there's any questions so far on this notion that there's a function that allows us to change the shape of the object by moving the vertices to a new location. Is there any questions surrounding this? We don't have Slido today, so chat window is where you're typing if you got a question.